Hello and welcome to the video. In this video, we will discuss a very important and non-ideal feature of a real-time circuit, and which is called as random noise. And it turns out that the dissipative components like resistors, MOSFETs, or some active components has some random noise, and components with no power loss, such as capacitor and inductor, don't have any kind of noise. So we will look noise in resistors in this video, and let's get started. So we will start with a random noise in resistor. So we will look at the definition and how to model it. So let's say we have a resistor and we have a current source. When the current source follows through the resistor, um, we have voltage across the resistor, which is IR, and accordingly, if we apply some voltage across the resistor, then we have a current through the resistor, which is V by R. So in reality, due to some random motion of charge carriers through R, it I is not exactly V by R. So what does it means? So let's say we measure the value of I through the resistor very precisely. So we can say we measure the I over time. So we get a mean value of V by R as a constant. But even though the current has the value of V by R as mean value, but there are minute variations, and we can say that the variations or the band is uh, due to noise, and at any time instance, any random time instance, the noise is uncorrelated. And for example, over here T0 and T1, so it is uncorrelated at T0 and T1. And if we do this experiment with two different resistors, the noise waveform will be uncorrelated and very random. So if we were to take a cross section of any resistor R, let's say this is a resistor and the current flow I flows through it, which is V by R. So when we see the charge flowing across the section, cross section, in addition to this mean value V by R, there will be some charges randomly moving back and forth because of random thermal motion of charges. Now we need a way to quantify this, and also to estimate if any we have to estimate it and eliminate it in any given circuit. So from the study of probability and random processes, we know what we can specify basically is spectral density, which is basically how the energy in the randomness is distributed over a frequency range. And we can specify a root mean squared value. In our case, it is 0, meaning a random process where root mean square is same as the variance or the standard deviation. And we know the average current is basically V by R, and rest of it is noise. And by definition, it will have 0 mean. Thus, we have to either specify the root mean square of the variance or root mean square of the standard deviation to specify the size of noise. So we have, let's say we have a voltage across R, and we have current, which is V by R. And as we discussed, we have a little noise, minute noise variation, I n. So this can be realized as like this exact thing can be realized as voltage across the resistor, which is a noiseless resistor, ideal resistor. And the noise in this resistor is basically noise current, which can be placed in parallel, and this can be realized or modeled as a current source. And there is no meaning of this direction of ion, and the mean value is anyway 0, and it is randomly flowing in both direction. Just to show a model, we have denoted a direction, but there is no meaning of the direction. And now if we look at the alternative description, so we had voltage across a resistor. Now the alternative description is there is a current flowing through the resistor, which will dissipate a voltage, not dissipate, form a voltage across this resistor, which is V equals to IR. And the noise can be moduled as Vn separately, and this can be thought as a current flowing through a noiseless resistor R and a series voltage source, which is Vn. So our V will be IR plus VN. So we assume that there is noiseless component which follows the VI relationship. For example, Ohm's law for resistor or square law model for MOSFET, and model out the noisy part as either a voltage source or a current source. From both alternative models, if we want the model, if we want to model out the noise as discussed earlier, this condition should be satisfied where current source due to noise times R is voltage source due to noise. This we can see very easily by assuming that, let's say we apply zero voltage across R. So there is zero voltage across the noiseless resistor R, and then we will get a IN as the noise factor or the current source due to noise, which can be modeled separately. We discussed it how over here. So we get some result if we use alternative model. Like let's say we are using the alternative model for current, which is basically a voltage source representing Vn for noise. So we get the same result, and we have a noiseless resistor in series with Vn. So the In will be Vn by R. Now, as we cannot specify the instantaneous values of In or Vn at any time instance, and thus what we do is we will specify the spectral density. For example, how the energy in Vn or In is distributed over the range of frequencies, and we know that, like, not we can say that equivalent voltage source of resistor divided by equivalent current source of resistor, basically noise of resistor R, is basically Vn In equals to R. So this comes from this condition, which must be satisfied. So what do we mean by spectral density? So spectral density of In and Vn is a function of frequency, and we consider only positive frequencies, as when we consider negative frequency, we just get a current image, current, like, mirror image of the curve. So it tells us the spectral density of In in some function of frequency, and we denote it by SI of F. So if we plot SIF versus frequency, which is basically a function of frequency, and like spectral density is some function over a frequency range. So uh, also spectral density or SIF is related to autocorrelation function of this process In through the Fourier transform, and the integration of SIF df from 0 to infinity gives us the variance or sigma square, and by taking the root of this variance we get the root mean squared value or the standard deviation. So now when we plot the curve, we get a constant noise, or this constant value of SIF over all frequency range. And in case of a resistor, the plot of spectral density versus frequency is a constant line, which also is called a white noise, and whose value is 4 kT by R. We'll see now how. So the magnitude of 4 kT by R is basically the magnitude of the white noise, or the constant value of SIF over all frequencies, where K is the Boltzmann constant and whose value is this, and T is the absolute temperature, 300 Kelvin. We also know that Vn equals to In times R, and because basically the spectral density relates to the square of these quantities, so we can say that Sin times R square is nothing but SVN, and this is spectral density of Vn, so voltage source due to the noise. So SVN is basically 4 kT by R times R square, so it is 4 kT R, and when we plot SVN against the frequency, there is a constant white noise of the value 4 kT R, where kT is 4 into 10 to the power minus 12 joule at 300 Kelvin. This is not 2, this is 12 minus 12. So basically For example, we calculate it for the resistor 1 kilo ohm. So SVN comes out to be 4 into 4 times 10 to the power minus 21, which is multiplied by the resistor and comes out to be 16 into 10 to the power minus 18. And the units are voltage square divided by hertz, as it is across the frequencies. And voltage noise is specified in voltage square by hertz, as it is related to the square of voltages, and spectral density obviously is related to the density over a frequency range. Similarly, SIN is given by the units ampere square by hertz, or 4 kT by R times, not times, but this is what the relation is, and given in the units of ampere square by hertz. So for example, we have 1 kilo ohm resistor. So SIN for that resistor will be, by calculation, 16 into 10 to the power minus 24 ampere square by hertz. These results were derived by Nyquist and proven experimentally. And we have the abstract definition of noise in terms of spectral density distribution over a frequency. But in circuits, we have signal in terms of voltages and currents. So that's why we converted our specified noise in the terms of voltages and current sources. And then we can compare our signal to the noise and see if it is sufficiently above the noise or not. So what exactly spectral density means? So let's take the SVN for the resistor R, which is modeled with a noiseless resistor in series with a Vn, which is due to its noise. So when this is passed through a band pass filter or any system, so let's say the system is band pass filter with a bandwidth of B, and the V out is taken. So basically what we are saying is, so Vn has its own SVN, which can be plotted against frequency, and at F naught we have a center frequency for the band pass filter, and we know that at this frequency this is our bandwidth through which our frequencies are passed, and we know that our SVN over a frequency is a constant value of 4 times KTR. And basically the variance for V out, so the variance for V out can be calculated by SVN times the bandwidth. For instance, let's take 1 kilo ohm resistor as the value of R, and thus the SVN is basically 16 into 10 to the power minus 18. And if we pass it through ideal band pass filter of bandwidth 1 megahertz, then 16 into 10 to the power minus 12 volt square is what our variance comes out to be of our V naught. And by taking the root of our variance, we would specify the RMS value, which is nothing but the standard deviation. And when we take the root of it, we get 4 micron volts as our standard variation due to noise. And it turns out that distribution of this noise is also a Gaussian. And let's say we have resistor R and current I flowing through the resistor R. It will have the mean value of I times R, and this is the mean value of I times R. And basically the deviation we calculated over here is 4 micron volt. So this is our probability density plotted against the voltage, and it gives us a Gaussian curve. And the probability density function with respect to the voltage plot will have the distribution around I times R. And by distribution we mean, let's say we have thousands of these circuits where we are passing current I through a resistor R, and we measure the voltage across all of them at the same time. Then we will find that all of them will not be equal to IR, but they will be having a mean value of IR and will have a distribution around it. So, and the standard deviation of the distribution is 4 micron volts in the case of 1 kilo ohm resistor at the bandwidth of 1 megahertz. So it also means that if we take any one of the circuits and pass the current I through the resistor R and measure the noise, and let's say we measure the noise in 1000 time instances, then it will also have a mean value of IR, but all the 1000 time instances let's say they will have a distribution around IR, and the standard deviation of that distribution will also be 4 micron volts. Thus, we cannot specify noise at any particular time instance or instance of time, but we can specify the RMS value and draw conclusions from that. And given that the distribution is Gaussian, we can say that 99.9% of the time the values will be lying within the range of plus minus 3 sigma. Sigma is the deviation, and basically our deviation is 4 micron volts. So if we pass current I through a resistor of 1 kilo ohm and bandwidth of interest is 1 megahertz, we will have a standard deviation of 4 volts, 4 micron volts, and 99% of the time we will get a voltage within plus minus of 12 micron volts of the value IR. So because now let's say because we deal with currents and voltages in our circuits and not their square values, the spectral density is also sometimes given in volts or amperes per root hertz. So basically what we had was SVN in the terms of 4 kTR, which had units of voltage square by hertz. But we deal with currents and voltages and not their squares. So what we can equate it to is sometimes it is given SVN as root of 4 kTR. So the units becomes voltage divided by root of hertz. So let's say for 1 kilo ohm resistor, we have the root of this value, which is SVN, which is given as 4 nanovolts divided by root of hertz. So at let's say at 1 megahertz bandwidth, we will be getting 4 nanovolts by root hertz multiplied by the root of bandwidth and not bandwidth. So after doing the calculations, we will get 4 micron volts as our result, which was the same. So similarly, it goes with SIN as well. And now let's take a resistor of 1 kilo ohm and plug it to an oscilloscope. Now, let's say this is an oscilloscope, and on oscilloscope, we will get a reading. Now, the oscilloscope ideally should not show anything as there is no voltage across resistor, right? But due to some random noise, it will show some band or some random fluctuations of voltage. And how much will that fluctuating voltage be? That is the question. So as usual, we cannot measure it for an instance, but we can specify the size, and the oscilloscope itself will have some bandwidth. Let's say 100 megahertz is the bandwidth of this oscilloscope. So the resistor has spectral noise density SVN equals to 4 kTR, and for 1 kilo ohm the value comes out to be 16 into 10 to the power minus 18. And from here we can calculate by taking the root mean square of our variance, and it comes out to be 40 micron volts. So we will see a band of some thickness which is plus minus 3 sigma, and where this value of sigma is 40 micron volts on an oscilloscope. And in our case, we have the deviation of plus minus 120 micron volts, and this is the noise we see on the oscilloscope. So now when Vn is basically a voltage source due to the noise passes through some circuit, it may not experience a transfer function which is a constant over all frequencies. So until now we said that it is a constant white noise over all the frequencies, but it may not experience a transfer function which is constant over all the frequencies. So in general, we have a transfer function h of f, which varies with frequency. At input, we apply Vn, which has SVI. So let's say SV of input, and at the output we have V out. So we have at the output SVO, and let's say the input spectral density is SVI and the output spectral density is SV naught. And we can integrate, or let's say we can find SV naught equals to SVI times magnitude of HF square, as SV are SVN or SVI are squared values and uncorrelated values. So we can find that SV naught is equals to SVI times magnitude of HF square. Now, if we want to calculate output spectral density, we have to integrate SV function of f df from 0 to infinity. And we know SV naught F is basically SVI times square of the magnitude. Now we what we'll do is we connect a resistor R, and then SVN is per input is nothing but 4 kTr, and SV out is 4 kTr times square of the magnitude of transfer function. And from here we get the mean square value as 4 kTr integral of magnitude of HF and its square dF. So just like any other voltage or current in a circuit, the noise voltage or the noise current of the resistor experiences a transfer function when it goes from input to the output. And now um, let's say over here we had only one resistor, but now let's say we have multiple noise sources in a circuit. So what we do is we calculate the transfer function from every noise source to the output. Let's say we have Vn and In sources, and input to them is 0, so the output will not be 0 due to the noise. So we have these noise sources. To calculate the output, we calculate the transfer function from every source. So basically, to calculate the V out, what we do is we have V1 times the H1F, which is transfer function for this. We have V2 times H2F, and we have I3 times H3F. And to calculate the spectral density, we have SV naught equals to SV1 times square of the magnitude of H1F and so on. So now this noise is expected to be very small quantity. So any calculation regarding noise will be linear even if we have a non-linear circuit, and small disturbances can be represented by a equivalent linear circuit. Hence the superposition always applies, and using superposition we can solve this equation. So Vn and Vn2 and In3 are uncorrelated with each other, and thus we can add up the spectral densities of individual contributions. And in fact, we have physically two different resistors. The noise from each resistor is uncorrelated, and let's verify it by taking a simple example. So we have this structure over here where the noise through this resistor is represented by In separately, and it has SI of 4 kT by R1. And similarly, we have R2, and it has a SI of 4 kT by R2. So if we have R1 and R2 in parallel, so it will somewhat look like this. And let's say two resistors in parallel will give us 1 upon R equivalent is equals to 1 upon R1 plus 1 upon R2. And the current will just parallel currents adds up. So it will just go by IN1 plus IN2. And this will give us the spectral density of 4 kT times 1 upon R1 plus 1 upon R2. And what we can say is basically when we say that there are two parallel resistors R1 and R2, so we have in total R effective and we have IN. So SI is in that case will be 4 kT times 1 by R effective. And we know the value of 1 by R effective is exactly equal to 1 upon R1 plus 1 upon R2. Thus, these two conditions match, and that's why they are consistent with each other. And thus, we verified that if we have physically two different resistors, the noise from each resistor is uncorrelated. So now we will take a simple circuit with a transfer function which is not a uniform transfer function with frequency, and let's take a circuit of first order RC low pass filter. So what we do is we have a input voltage, we have a RC network, and we know the transfer function V naught by Vi is 1 upon 1 plus SCR. As usual, there will be noise due to R, and C never adds the noise as it does not dissipate any power around it. But we have the noise due to R, and we would like to find out the output noise. As we said earlier, noise is calculated from small signal linear equivalent circuit, and we can do that without the input signal or a large signal, as a linear circuit follows superposition. So if we want to find the effect of noise and the large signal together, we will find them separately and then add up. Of course, there are circuits which this way is not valid, as the behavior of noise totally depends on the presence of large signals. But in most of the cases, we can just set the large signal value to the 0 and calculate the small signal noise. So what we'll do in this case is now set the Vi or the large signal to 0. We will take the voltage source due to the noise as Vn. We have R, we have C. So we will take a transfer function which will be 1 upon 1 plus SCR. So now instead of Vi, we have Vn. And now when we do calculation for noise, we analyze, what we do is we always replace omega with 2 pi f, as we know that we represent everything as a function of f while doing the calculations for noise. So V naught of f s divided by Vn of s, or basically V naught of j 2 pi f divided by Vn of j 2 pi f is 1 upon 1 plus j 2 pi f c r. And we know SV naught is equals to SVN times magnitude square. So if we put the value of magnitude magnitude squared, so what will we basically getting is, from this equation we can say that at lower frequencies it has a magnitude which is almost equal to 4 times KTR, and at very high frequencies this becomes infinity and it drops to almost 0. So bandwidth when frequency is 1 upon 2 pi CR is basically SV naught. Like we have bandwidth when f equals to 1 upon 2 pi CR. If we put this value in our SV naught, it comes out to be 2 KTR. So what we say that at the bandwidth f naught, the value of our curve is nothing but 2 KTR, and it will start with code 4 KTR and it will go to 0. So the mean squared value or the variance of output noise is given by integration of SV naught as a function of f times df. And if we put the value of SV naught and we integrate it, so we will get the mean squared value as kt by c. And apparently this noise seems independent of r. Interesting. So basically we calculate the transfer function from resistor noise to the output, and if we have many resistors, then we calculate the transfer function for each resistor and add them up. We have discussed about that, but what fascinates is the mean square value is independent of resistor value r. Now we know the noise is nothing but the spectral density multiplied by the bandwidth, and as spectral density increases, the value of resistance decreases, and as the bandwidth decreases, the value of resistor increases, and it increases in co-parallel way. So thus the product of these two happens to be independent of r, and which is basically equals to kt by c. So our variance is kt by c, and the larger the capacitor we will use, the smaller the deviation we will get due to the noise in the resistor. So let's take an example where we have a value of capacitor, we have a value of resistor, and thus from here we will get our bandwidth of this value and our spectral density of this value. So when we plot it over here like this, and we have our bandwidth over here, so it will be 2 times KTR. This is 4 times KTR, so it is half of it. And now if we make the resistor value twice of its value, so basically 200 kilo ohms, then what will happen is bandwidth will become half and SVN will become double. So initially we had this curve, and now what will become if we increase the value of R, the bandwidth will become twice, and sorry, the bandwidth will reduce from this point to half of its point, and the spectral density will become twice. So, and it will go to 0 like this. So it turns out that our noise variance is nothing but the area under this curve, and this area is for the curve with resistance 100k, and this area is for the curve when the resistance is twice. So it turns out that the area under the curve, and even if uh, r changes to twice its value, the areas under curve are equal. So area under this curve is equal to the area under this curve. So basically, regardless of the value of resistor in a RC circuit, we will have a noise of KT by C. So that's all for this video. Thank you for watching.